This Week in the Shop, episode number 2. While the machines are running all the parts that are getting restocked, my goal is to finish programming the 20 valve covers and machine the first one this weekend. Let's see where we're at. So we made the 16 valve covers for a couple years now, and the machining process is pretty dialed in. We start by machining the underside of the 16 valve cover, and then a solid chunk that fits the inside goes inside of it. Then it goes into a vise that squeezes it, and then we machine the top side. The 20 valve cover is a little bit too wide, top to bottom, for me to comfortably put something inside of it and squeeze it. What ends up happening when you squeeze something that's big like this is that it actually deforms, and this center section right here would actually kind of bulge up in the middle, and I didn't want that to happen. So the programming on this 20 valve cover is opposite of the way that I'm doing the 16 valve covers. So I started with the first operation being the top side, and luckily the 20 valve has holes for mounting the center cover, and I'm going to be able to use those holes to bolt a fixture to be able to flip it over, hold on to the fixture in a vise, and then machine the inside out. So all of the programming is now finally done, the top side and the bottom side. Let me show you what it's going to look like. So the fixture that I made that's going to go for our second operation is this right here. What it's going to do is it's going to locate on these two flat surfaces, the top of the valve cover and the top of the step, and then it has these bosses that stick out, and these are going to be a pretty precision fit into the valve cover itself, into these locating holes right here where the valve cover grommets go into and hold the valve cover down. So that'll give me a good relation for when I flip the part over. I can make sure that as long as that fixture indicates in straight, I'll know exactly where the valve cover is so that I can machine the other side and have it match up with the first side. I'm not going to go into the details of every single toolpath, but just to give you an idea of the generic strategy for machining a part like this, the outside or the top of the valve cover is pretty easy to do. What you end up doing, and I'll show you the toolpaths here, this green block represents the material. And as we begin to machine it away, we start by surfacing the top, which is a operation that's done to give us a reference so that we know all of the tools that cut after it are going the right depth into the part. And then I'm just going to use a 1/2 end mill to rough out the outside shape of the valve cover. Now there are other ways to do this that could potentially save time and be a little bit faster, but when I'm doing prototypes, I try to stick with the toolpaths that I'm most confident are going to give me the result that I'm looking for. So I don't want to necessarily try something that's way too aggressive and then run into an issue when I'm doing a prototype. So I'd rather a cycle time be a little bit longer, but give me the result that I want so that I do have a finished product in hand that I can make adjustments to, rather than trying to optimize my toolpaths but potentially scrap the piece of prototype material. After the shape is roughed out with the 1/2 end mill, then I'm going to go around the outside of the part and do all of the surfacing with a 3/8" ball end mill. This is a long tool that is neck down and only has cutting flutes on the bottom 1/2 inch of the tool. So it's sticking out far, but is also rigid enough to leave a nice finish. So this is going to go around the entire part and create the finished surface of the outside of the part. That last toolpath that was going around the outside of the part is called a waterline toolpath, and it does a circular motion with a preset step down amount. So for example, I think I'm stepping down about 20/1000ths of an inch. And this works really good for the sides of parts. So anything that's real vertical works really good with a stepping down toolpath because you can really control the distance between each of these stepping lines. Where it doesn't do well is on horizontal surfaces. So luckily the top of this valve cover was cut with a face mill, so it's going to have a nice finish. But if you look closely, you can see that near the top of the valve cover, the steps are uneven here because while it does step down 20/1000ths, it has to step over more when it's more horizontal. And on the horizontal surfaces, sometimes that leaves these like anomalies here, like this weird pyramid looking shape. and then you have to go back with another toolpath and go in a different direction or a different style to get rid of those. So the next toolpath that I chose, sorry, this is a contour. But the next toolpath that I chose for doing this top surface is just a flow line toolpath, which is a directional toolpath across a surface. Kind of like a parallel toolpath, which is just an angular surfacing motion. The flow line follows the surfaces in a direction that you're choosing. So instead of choosing an area to do the machining on, the flow line toolpath is based off of a surface specifically. So where a parallel toolpath would have to be constrained with a containment boundary, the flow line toolpath just follows the surfaces that you select, and you don't really have to contain it at all. So you can see that this toolpath is doing a good job of getting rid of all those anomalies on the front of the valve cover, and it'll leave these nice consistent lines across the front of it. For the top of the valve cover, in person, this is actually not going to look very bad. So I'm going to leave this the way that it is, and I'm going to machine the first one. And if for some reason those steps really stand out or don't look right, then I can go back and adjust the step over or even change the strategy. But for the prototype, I think this is going to look fine. So once I'm happy with the way that all of the machining looks on the first side through this verification, you can see I even added a little logo on the back side here. Then what I'm going to do before I verify the bottom side, I'm going to save this as its own file so that I can reference it. And the reason that you want to do that is because while the solid model is a good reference for machining the other side, a lot of times the machined part doesn't exactly meet the solid model that you've drawn. And you want to see if things are actually blending with the machined part, not just whether or not they represent the solid model or the drawing of the part that you've made. So I saved this, and let me show you what it looks like after it's saved, and then we start machining the other side. So just like on the first side, the original stock was a green color. When I bring in this file of our first side machined, it also comes in green. That way we can see what's cut away from it. It'll show up in yellow. So this is a pretty accurate representation, including all of the different tool marks and blended areas and little steps around the surfaced areas. This is a pretty close representation to what the part's going to look like after the first operation. So we use this, and then we can go ahead and verify the second side. The second side is going to start with the facing, and then I cut the O-ring groove or the gasket groove with a little 1/8 inch end mill. I like to do this first because if I cut away the areas that go over the cam caps, then that 1/8 inch end mill, as it's ramping through this valve cover gasket, becomes interrupted in between these areas where the cam cap area is. So it would be coming around here, an 1/8 inch end mill would be ramping down, and as it exited right here, it would be out of the cut, and then it would have to abruptly enter the cut again as it went back into that grooved area. And that can, while most of the time it's probably okay, it can cause additional stress to the tool exiting and re-entering. So I like to do the gasket groove all by itself first so that there's a constant load on the tool all the way around until it's done. This toolpath is called an area clearance toolpath, and if any of you guys are into 3D printing, you'll kind of recognize what this is doing. This is a lot like a slicer program. What this does is it's going to take an image of the part in a step down that you're saying, and I think, for example, let's call this 75 thousandths of a step down, and then it's going to use a 2D toolpath to pocket out everything that isn't the part in that depth. And it's going to go all the way down to a preset depth that you tell it to go to. So again, this is not the fastest way to clear all of this out, but this is the safest and easiest way to cut away as much of the material as possible with one simple tool path and without any problems. As we get further down roughing into this part, you can start to see some of the green showing through. And this is why it's good to bring in the represented first operation so that you can see what areas are getting cut into and what areas aren't cutting. If you look over on those breather threads on the backside, you can see that the beginning of that thread is actually cut into with the roughing operation. And so I'm probably going to go back in and block off those holes so I don't have to worry about the roughing tool going down into those areas and damaging the threads. Probably one of the more difficult parts of this is cutting out the valve cover gasket groove around the cam cap area. And because it's in a vertical position, you have to use very small tools, and they have to be extended really far to be able to reach down inside of this groove. So what I ended up doing is roughing it out first, and then I'm taking an 1/8 inch ball end mill and I'm finishing the chamfers around the edge of the groove first before I cut the inside of the groove out. This 1/8 inch ball is actually pretty strong, and because it's mostly doing a downward motion, I feel pretty confident that it's not going to have any trouble cutting away those chamfers. And that kind of gives me a roughed, let me see if I can see here, a roughed out groove that I then only have to go back in and finish the inside or center part of it. And what I do with that is an 1/8 inch end mill with another waterline or stepping down tool path. And what that looks like is this. You can see what this is doing is it's leading into the groove area and then stepping down and then stepping out. And then it goes back over and does it again. This is to maintain that every time the tool is entering the cut, it's climb cutting, which means it's rolling or cutting in the direction that the tool is spinning. Now this is a pretty delicate tool here now. This is the 1/8 inch end mill, and it's almost channeling as it goes in here. So this puts quite a bit of side load, so the step down is really small. This is probably gonna take, I don't know, 3 or 4 minutes to machine just this part. So lastly, before we go out into the shop to see what's actually happening, I wanted to cover the baffle. So originally I drew this cool louvered baffle, which I really like the design. It fits on the inside nicely and looks cool with the louvers. But the difference between a louvered baffle and, let's say, a baffle with some holes in it is that this baffle with the holes in it can be cut out on a laser, and the baffle that has louvers has to be cut out on a punch. So for prototype, which I really only want to make a couple of these just to test the concept, cutting out on a punch requires a lot more programming, and so the initial cost of purchasing these baffles in a quantity of, let's say, 2 or 3 is very expensive. So what I'm doing is I drew up the laser cut baffle, and I'm going to have a couple of those cut out so that I can do my testing. And then after, assuming that I still want to do the louver baffle for the production run, which I'm probably actually like 50-50 on now, then when I have a big order of 40 of them or something, then I can justify the setup cost and programming cost of having them punched with the louvers so that the individual price is not that high. So the prototype the prototype baffle is probably going to look like this with the holes in it. So this is totally programmed now. I'm going to be picking up the material tomorrow, and my goal is to machine one of these complete over the weekend. So you should be seeing a machine valve cover in episode number 3. But anyway, let's go out to the shop and see what's happening in the shop currently. Sorry, one last thing in the office before we go into the shop. This was dropped off the other day by a friend. It comes from Dee's Speed Shop, or Dennis from Dee's Speed Shop. He lent me this bracket. This is a non-power steering AC compressor bracket for 4AG engine. And these are getting a bit expensive for guys that want to have air conditioning on their car but don't want to have power steering. So let me know if you think it'd be a good idea to machine one of these out of billet to make them available for anybody that wants one but doesn't want to pay the OEM prices that are going right now, which is I think about $400 or $500 for the bracket. Let me know. So last week we were machining these threaded rods in our Miano. These are for reverse lockout shifters. Take a look at this. This is an M12 thread on a stainless steel rod. Both ends are machined. There's a chamfer at the bottom. Before these get bagged or bent, they go through a deburring process on a 3M Scotch-Brite wheel. And I just run the tops of the threads on this to get any potential burrs that are still on there. They're machined pretty nicely. There's not much of a burr on here, but just to sort of roll over the top of the thread, it makes screwing on your shift knob just a little bit easier. And then depending on the condition of the stainless steel rod, sometimes I'll also do a light sanding on the outside of the rod itself to give it a uniform finish. This batch is actually pretty clean, so it might not need it, but we'll see once I actually start deburring them. So I'm going to get to this later today. Out on the DM2 table, all of those reverse lockout stops are done. Those BA4 rear subframe braces are finished. Those are back on the website if you guys are interested. This is the material for the tension rod spacers for the A86. We use these to lower the tension rod mounts so that when you lower your subframe, you can also lower the tension rod mounts so they stay in line with each other and the suspension geometry doesn't get wonky. So I need to set these up in the DM2. These will be running for the next day and a half or 2 days. And then we will move on to, probably in this machine, I'll be doing the valve cover fixture for the op tube. Over in the VF1, we're still doing shift knob inserts. These are the OG inserts still. Sorry, a little bit dirty. We've just about finished all the M10 1.5 threads, and we're going to be moving on to, all of these are going to be M10 1.25. So this is sort of your Honda thread pitch, and this is going to be your Nissan thread pitch. If you look closely in these inserts, I don't know if I'm going to be able to get this or not. I actually engraved the thread with a very tiny tool on the inside. You can see M10 1.5 on this one. So if you have one of our OG shift knobs that was made in the last 2 years or so and you're unsure of the thread, just look inside and it should have the thread pitch engraved. In the VF2, we're still running K24 mounts. I finished all the passenger side mounts yesterday, and this morning I set up these driver side mounts. These are the mount bosses that attach to those base plates from last episode. So the way that we run these bosses is the first operation over in the vise here is just going to cut, let me blow this out. It's just going to cut the mounting area of the boss itself. You can see we engraved what boss it is, K24 driver side. This is cutting down the top of the material. It's going to cut down 1/2 inch of the outside of the part in a rough state. So this is not a finished surface here. And the reason that I cut down 1/2 inch down the top of the part instead of just drilling the holes, let me show you why, is because I want to be able to get a tool in back behind here so that I can cut away all of this material. And if I don't cut about 1/2 inch down off of the bottom of the part, I'll end up sort of plunging my tool into that raw stock or raw material. It just gives me a little bit of safety and clearance for when I'm machining around past the bottom of the part in my fixture. And you can see here, this is how we are doing these bosses. The boss starts in the vise, and then it gets moved over onto the 4th axis. The second operation machines this side of the part, finishes all of this, and then the 4th axis rotates around to the other side. And then all the tools come down from the top here and machine all of this side of the boss. And then lastly, the 4th axis rotates just so that the surface where your engine mount attaches to this bracket lines perpendicular with the spindle. Then we can go ahead and face this and cut the holes for the mounting of that mount. And since this is just finished, I've only made 2 of these so far. So still got quite a bit of these to go. It'll be running for another 2 days or a day and a half or so. So lastly, to wrap up the episode, I'll show you how one of these engine mounts is assembled. These bosses have holes that are reamed to a precise size for these dowel pins so that the boss locates precisely onto our base plates, which also have these reamed holes. So the first step for assembly is to hammer in 2 of these dowel pins. I'm going to do that right now. Here's what they look like after those dowel pins have been hammered in. And let me show you. So we grab a base plate, and then it goes on top of the mount. The fumble. And then these dowel pins allow it to locate very precisely and locks it into place. So that is very accurately located. There's no play at all. And then we could take these flathead metric screws, which we have Loctite applied on before they go in. And then all the screws go in, and then it gets torqued together. These are flathead screws so that they sit flush with the backside of the base plate so we can bolt it up to an engine block without having to counterbore for a socket head screw. This allows the mount to be a little bit stronger this way. And just a little torque. They all get torqued. And then got an engine mount. This is our K24 engine mount for driver's side for mounting a K24 into an A86. All right, see you guys next week.